Welcome. This is the machine learning course, the CS 485. So this is CS 485, 685 machine learning. My name is Shai Ben-David. So let me start with some administration things. So I guess the first question people ask is about the course mark. So the mark is going to be 50%. So we're going to have assignments, and that's going to be 4 assignments times 12.5%. So this is 50%. And we are going to have a final, which is going to be another 50%. And you have to pass the final to pass the course. So, and this is for the 485. Do we have here any grad students that take it for credit as grad students? Okay. So for grad students, for the 685, the composition will be a little bit different. So the assignments will be only 30%. The final will be 40%. And there will be a project for 30%. And for undergrads, there is also an option of a project that will be 5 points bonus. So you can get a 5 points bonus for a project for the undergrad. So this is plus 5 bonus for a project. And projects should be on individual basis. My email is shai@Waterloo. My office is 1311, and the office hour is going to be Wednesday right after the class. We are going to have 2 TAs. There will be a web page where you see all the information. So I don't have the office hours yet. So there's going to be a web page. There's going to be a web page on Learn, but also a web page which is open to everybody. And as you see, the class is going to be recorded. So I will try to post the recordings of the class as soon as I get them from the IT services. For the book, we now have a textbook, and we are going to follow, almost all of the course is covered by the textbook. And the textbook is called Understanding Machine Learning. And it's by Shai Schwartz and myself. So this is going to be the textbook. It should be available at the university bookstore. So you don't really need to take notes. Most of the stuff will be in the book, and then the lectures are recorded. And I really recommend not to use laptops during the lecture. Okay. Any other questions about administration stuff?
Sorry, what building is your office in?
Oh, this is the DC. Okay. One more comment about I don't know how many of you have taken a course with me before, but I really encourage questions, comments. The more the better. If you don't feel that you are slowing me down, if you don't understand something, ask, because most likely there are other people who also don't understand it and will appreciate that you slow me down and make me explain it. If you slow me down too much, then I will cover less material and there'll be less stuff to learn for the exam. So you only gain from it. And one more thing that I do usually to encourage comments is that if you find a mistake on the board, not a spelling mistake, but a content mistake, and you comment in class, then you get a bonus point. So if you find 100 mistakes during the course, you are completely covered for the but and if you comment on something and it's not a mistake, then you are completely protected by anonymity. I don't know your name. There's no record of it. So try your luck. Okay, more questions? Yes?
Which software are we going to use in the assignments? MATLAB or Octave?
So yeah, I will get to it soon, but this is a theoretical course, and that's very important to understand. There is no programming. There is no, and the assignments are going, it's a mathematical theoretical course. So although machine learning is something very applicable, this course is about the theory of machine learning. So the assignments are going to be mathematical assignments. I mean, it's nicer. I mean, the most sophisticated software that you may need to use is later for typing down your assignments. Okay? And this is also important, I think, as a warning, maybe before we even start describing the course. I mean, it's a theoretical course. I'm telling nice stories, but at the end, it's a mathematical course, and it's not trivial. And if you're here just to get ready for your startup in machine learning, then it's probably not the right course for you. It is really for what the name of the book, Understanding Machine Learning, to understand the principles, to understand the basic tools, but it's not about implementation. It's not about getting skilled in using machine learning. It's about understanding the concepts behind it. It will eventually, it is very practical, it's very applicable, but the focus of the course is on the mathematical aspects. So, I mean, every year that I teach this course, at the end of the course, I get the students' comments, and there's always a significant portion of the students that complain. The course was too theoretical. So I'm warning you right now. The course is going to be too theoretical. And if it is not what you're looking for, then maybe it's not. I mean, you're welcome to sit in on it, but just be aware of this. OK, so let me start by talking a little bit about learning. So what is learning? What is learning? What is machine learning? So what is learning? And one way of describing learning is that learning is the process that takes us from experience and leads us to expertise. So you encounter experience in some domain, you see more and more examples of it, and then you become an expert and you can give advice. So, and machine learning is we're trying to take this process of turning experience into expertise and program it. So we are going to, the machine learning program is a program that takes some kind of experience, some kinds of data that you can collect, and try to turn it into expertise. So what is an expertise? Expertise for us usually will be another program that can do some things that you need the expertise to do. We will see many examples, but maybe for the simplest running example, think of developing a spam filter. So the spam filter gets experience by looking at emails that are marked whether they are spam or not. That's the input to the program. The program then comes out with another program, and this new program is the spam filter. This program, when it sees an email, marks it as spam or not spam. But this program is the one used to take emails that are already marked and come up with a program that is going to be the spam filter. So what we are going to talk about in the course is exactly analyze each of these components. What exactly do we mean by experience? How much of it do we need? How is the program going to run? What resources the program is going to need? The learning program, what can it do, what can it not do? And when we come to the expertise, we have some output. How do we evaluate? How do we measure its success? What kind of program do we want to output, and so on. So these are the components that we will try to understand. OK, so let me start. If we want to talk about learning, let me start by learning in nature. Just to give us some direction. So one of the first examples that I want to talk about in learning in nature is the phenomena which is called bait shyness. So what is bait shyness? Bait shyness is a phenomena which happens with rats. If you try to poison rats, it turns out that it's very difficult. Why is it difficult to poison rats? Because if you distribute around your yard some kind of baits for the rats, the rat, when it will notice that there is some kind of food that it's not used to, it's different in its smell or in its shape than things that it usually eats, it will take only a very small bite from this new suspicious food. And then, if the rat feels sick a few hours later, it will associate the sickness with this novel food and will never touch it again. So it's very difficult to eliminate rats by just distributing baits because they have this bait shyness. Now, this is clearly a very impressive example of learning. The rat sees the new food, tastes it once, and from this single experience, it learned something. It learned that this type of food is poisonous and it should not touch it. So that's a very positive, a very strong, successful example. And we want to kind of be able to imitate it. So if we want to for example, develop, so I'm not going to talk about how the rat does it at this point, but let us talk of a similar example of something that we want to do. So if we want to develop spam filters. So in that case, our input is we get emails. So you get email 1, and it's labeled spam or not spam. Then you see email 2, and say it is labeled not spam, and so on. You get a collection of emails that you are training on, and you have to come up with a program. So how can we design a program like this that will do this kind of job for us? So maybe the simplest way of doing it is to say, I will memorize all the emails that have been recorded as spam, just like the rat does. It memorizes all the food that it tasted and concluded that it was poisonous. And whenever I see something that is like this, whenever the rat sees something which is like the food that she saw, then it will not touch it. So I can try to use the same strategy for spam filters. I will memorize all the emails that were detected as spam. And when I see a new email, if it's one of those that I already marked as spam, I will raise the flag, it's probably a spam. And if it's an email that I haven't seen before, it's probably not spam. So what's wrong with such a program? Yes?
You're very rarely going to get two emails that are exactly the same.
Right. I am hardly likely to get two emails which are exactly the same. So the problem with, so the first kind of approach is memorization. Memorize. Is maybe the simplest approach to learning. Just memorize everything that happened in the past. If you come across exactly the same situation, you know what to do. But the problem with memorization is, in the words that we use, in the terminology that we use in machine learning, the problem is that it does not generalize. So we have a very important aspect. We want our what we learned, we want it to generalization. That's a very important feature. So what do I mean by generalization? I mean that it can be applied to data that I haven't seen before. So if I just memorize the emails, it will not generalize. Because when I see an email that I haven't seen before, I cannot take my old experience and extend it to learn something about the new type of email that I didn't see before. So memorization may be the first approach to trying to learn. We definitely do it, but it's not enough. Because just memorization will not generalize to cases that we have not seen before. So the first challenge from learning is to go beyond memorization and find something that can generalize. And generalization is called sometimes inductive reasoning. So inductive reasoning is reasoning by which we take previous cases and try to extend it to something new. This is different from deductive reasoning, in which we just look at all the logical consequences of what we've seen before. But here we not just look at logical consequences, but we want to, in inductive reasoning, try to generalize it to new cases that do not necessarily follow from the old cases. So this is what we are trying to do. We are trying to get generalization. We are trying to do inductive reasoning. And let me go to another example from nature. An example of generalization. And the next example that I want to consider is pigeon superstition. So pigeon superstition is a very entertaining phenomena. It was discovered by Skinner in 1947. So Skinner was one of the biggest, most important psychologists of the first half of the previous century. He worked a lot on behavioral psychology. I mean, okay, well, we will not get into a discussion of psychology, but just in one sentence, there is the kind of the Freudian school that tries to look at the human as something very special and try to do psychology based on all kind of special, not only the human is special, but every individual is very special. On the other extreme, there is this behavioral psychology that says people, animal, it's all the same, and it's just a black box. We don't really try to understand what's happening inside. We get some input, we get some output. We are trying to learn the connection between them. And behavioral psychology takes this very kind of mechanistic approach, and Skinner was one of the founders of this direction. Anyway, let's go back to pigeon superstition and learning. So Skinner did the following experiment. He took a collection of pigeons and put them in a cage. I don't know how much I can draw it. So here is our cage. And here we have some pigeons. something like that. We have pigeons in the cage, and we also put in the cage all kind of different toys, different elements of color and shape. And above this cage, there was some kind of a mechanism that can spray grains. And what Skinner did is just at regular or random intervals, without any relationship to what the birds are doing, it will just suddenly have a rain of a short distribution of food. Now, what is happening to so the very simple experiment. You just put the pigeon in the cage, you put some toys around, and say every hour or every 2 hours, you just do one spraying of grains. It doesn't look like much is going to happen, right? But it turns out that something very interesting does happen. The birds are getting hungry. And when a bird is getting hungry, the way of a bird to look for food is to peck around. Usually those pigeons in nature, they peck for finding worms or something. So they start pecking around. Now, suddenly there is a spraying of food. Now the bird is prone to learning. It tends to suspect that maybe the toy that it was pecking at that particular moment had some influence on getting food. So the next time that the bird is hungry, the bird is more likely to peck on this particular toy than on others, because it made some association between this toy and the food. Now, the next time we spray food, it's kind of for every bird, there's a small tendency to reinforce what it already did, because now the bird was, again, pecking at the same toy and getting food again. So by doing nothing, just repeating this experience 10, 20 times, after a while you see that every bird is completely devoted to a specific toy that it believes is going to bring food, and just pecking it vigorously all the time. And each bird believes in its own random toy that this is really what brings food. Right? I mean, by calling it superstition, of course, Skinner had some message to humans as well, but we don't want to get into this. I can tell you from my religion that when you live in Israel, the rain is coming. There's no rain over the summer. It's a very dry country, and rain is a very important resource for the farmers. And the rain usually comes in the fall. And there is a holiday at the beginning of the fall where you say prayers for the rain. And indeed, after you say those prayers, it's likely that there will be rain. So this is called pigeon superstition, and this is also some type of learning. The bird did generalization. The bird generalized from previous experience the conclusion that pecking on this particular toy brings food. And this is a very kind of bad generalization. So here we got some kind of silly generalization. And with the rats, we got some very clever and very important generalization. This generalization in rats allows them to survive. It's very important for domestic rats to have this bait shyness. They learn something useful. The pigeons learn something silly. And what we were trying to understand is what distinguishes between these two types of learning. Both of them had some experience. Both of them concluded some expertise from their experience. But the expertise that the rats got is very useful. The expertise that the pigeon got is completely silly. So what distinguishes these two phenomena? So I'm not asking you to find out on your own, but I'll describe to you another experiment that was done much more recently than these experiments, and was trying to answer exactly this question. And this was done, another experiment done by a guy called Garcia. He was doing his PhD, I think, in Berkeley or Stanford. And so Garcia, 1996, much later, and he tried to understand better what distinguishes between those two types of learning. And he looked at the rats again. And he did the following thing. He gave the rat the bait, the poisonous bait, in a way that completely looked and smelled like the usual food that they get. So he just injected the poison into the kind of food that was usually there in the yard. But that's kind of an unfair game, right? To make the game fair, whenever the rat was trying to touch, he marked for himself which pieces of food are poisonous. Whenever the rat was trying to touch a poisonous piece of food, he will ring a bell. Now the question is, does the rat learn the connection between the sounding of the bell and the fact that 5 hours later it feels sick? You see, what we are trying to ask is, could the rat, when it gets sick 5 hours later, associate it with the fact that when it tried this food, there was a ringing of a bell? What do you think? Will the rats be able to learn it or not? I mean, there's no, I don't expect you, right? Just tell me what you think. Yeah, what do you think?
I think they would be able to learn it. It just seems like it happens at the same time, and then, you know, next time they go for food, they'll wait a second and just see.
But, yeah, what?
But they only take a small bite when they see something new, so if they see a food they've already seen before, wouldn't they eat a lot of it and just stop?
That's a very good point. I really don't know how he overcame it. It's a good point, because he really was trying to make it look like the old food and trying to see whether they learned something or not. And I had to check the paper again. It's a very good point. Right. But he did come to the conclusion whether they learned the association or not. Now, we all know about the Pavlov dogs, right? The Pavlov dogs are dogs that you ring the bell every time you give them a feeding, and after a while, once the dog hears the bell, the dog salivates. The dog knows that the bell indicates food. But there is a big difference. For the dog to learn the Pavlovian behavior, you need to repeat this experiments many times. For the rats, you only give them one chance. And the question is, could they learn from just one experiment the association between the ringing of a bell and the sickness 5 hours later? Yes?
I think they maybe won't, because in order to learn the association, they have to pick up on information that might be relevant, and they might not identify the bell ringing as any relevant.
Right. So the interesting thing is the rats fail to learn to associate the bell ringing with the poison effect. I mean, again, the key here is they only were exposed to it once, but they failed to learn. And we try to, why would they fail with the bell, but they succeed when the food has a different shape or different smell? And yes?
Basically, I think it's against their basic instincts. Like taking small bites is their basic instinct to detect if the food is right or wrong. Bell is something new for them, and they can't just learn them instantly.
Right. So what happens here? I mean, we can ask ourselves, how did the rats develop this wonderful skill? And the rats developed these wonderful skills through genetics, through many generations. Those that were eating poison were getting extinguished. But the point is that through this development, the new food, the dangerous food, always differed from the old food by its shape, by its color, by its smell. It never happened to them in generations of development of rats that whenever they were eating poisonous food, someone rang a bell. So what the rats had is they had some kind of prior knowledge So there is a key component here, which is prior knowledge. The prior knowledge of the rats it's kind of already programmed into their brain by generations of experience. And the prior knowledge is about which features are relevant or not. It kind of tells them when you eat a food and you want to know if it's poison or not, what you hear at that point in time is irrelevant. What's relevant is the taste of the food, the shape of the food, the smell of the food, but not the noise that you hear while you're eating. So they have some kind of prior knowledge about relevant information as opposed to irrelevant information. Now, you can ask, why have this limitation? Why not learn that pay attention to everything? Use all your senses, pay attention to everything. Maybe we can this way design an improved version of rats. What will be a deficiency in trying to pay attention to everything? And you see, the same thing happens to us. I mean, we experience in our life all the time with all kinds of things, right? And so if you come to someone and tell them, someone that you just never met before, and you tell them, oh, I find you so attractive, would you go out with me, without ever talking to them before, then probably you will get a negative reaction. But you will kind of associate it with what you said, right? You will not associate it with the fact that you did it at 11:02, and next time you will learn your lesson. Never try such things at 11:02. So there is an important component here of relevant information and what's not relevant. What will happen if we picked all the information and tried to connect it to anything new that was happening? What will go wrong? Yes?
We would develop some like false alert, right? Because there is always something which can seem important, but it's not relevant to that.
Right. So here the point here is that the rats have to the rats in the evening they feel sick. They have to kind of think about what have they eaten all the day long and associate the sickness with the feeding that was special. If I pay attention to every component, then every feeding is special, right? Today, when I ate at Williams, it was the first time that I was sitting in the window, by the window, and the person in the next table was having a scarf on the head. So if I feel sick, I will associate it maybe. So every single experience is special. If we allow ourselves to collect every possible feature, then everything becomes special. And now when you feel sick, you don't know what to associate it with. And therefore, this prior knowledge is very important. We could not have done without it. There's no way it would succeed without it. And the prior knowledge is going to be key in what we are going to do in machine learning. So, and the same for spam filters. From spam filters, we have prior knowledge. We know, for example, that usually the time on which you got the email is not so relevant to whether it's spam or not. But the question of whether there were too many capitals or not is related to whether it's spam or not. You know that some words are relevant to whether it's spam or not, but others are completely irrelevant. So we have a lot of prior knowledge that comes into the development of spam filters. And we can think, there is some kind of a continuum here, where I can have little prior knowledge. If I have very little prior knowledge versus much prior knowledge. So if I have little prior knowledge, I need a lot of training data in order to learn something in a completely new environment on which I don't have any prior knowledge. I need a lot of experience. When I have a lot of prior knowledge, very, very much prior knowledge, maybe I can completely write an expert system without having to look at experience at all. If I already know how to do something, maybe I can write my program without having to collect data. And machine learning is living somewhere here. We are trying to see how much prior knowledge we need and to trade it with the amount of experience that we will need to collect. So this is a very important coordinate along which we are going to look at different machine learning scenarios. Okay, so that's basically my introduction to what is learning, and our main conclusion is that learning has a lot to do with prior knowledge. Okay, why do we need machine learning? So that's another good question that worth paying attention to. Why do we need machine learning? Why do we need machines to learn? Why is it not enough that we learn ourselves? Why is it not enough that our machines will just be programmed but will never learn? Because we are really trying to talk here about programs for computers that allow the computer to learn. It's not something completely standard, right? We think about animals that are learning. We think about computers that get a program and just execute the program. Now we are trying to think about a computer program that can learn from experience. Why do we need such a creature? Yes?
Because computers can learn from a lot more data than humans can.
Right. So, yes?
I was going to say humans are just naturally biased, whereas...
Oh, so it can do a better job than humans.
Yeah.
Right. So let me add other... What? We're just too slow. So I think that there's several aspects, and each of them we will see some examples of. I think the first aspect is that, assume that I want a program, assume that I want a spam detector, and I don't want to use learning. So in order to write a spam detectors, I have to write a program that will be able to distinguish spam from not spam. It's too complex for me to write a program like this. Maybe when I see the email, I know it. But I don't have enough understanding of how I know it. So some tasks that we can do, that we or animals carry out, may be too complex to program. So examples like this is, as I mentioned, spam filtering, but I'll give you some stronger examples. Driving, speech recognition, so these are tasks that we carry out routinely. But if you have to write a program that will take the sound and get the meaning out of it, it is too complex for us. We don't know how exactly we're doing it. We're not completely aware of it. If I need to multiply two numbers, I know exactly what I'm doing. I can write a program that will do it for me. Why? Because I understand fully how I multiply numbers. But if I try to understand how do I take a sound and extract a meaning from it, or extract text from it, it's way too complicated. So we have very good speech recognizers, but they are all based on machine learning. We cannot program, we cannot write ourselves the program that will detect text from voice, but we can have a program that learns. It says a lot of examples of sounds and the corresponding text, and the program learns. So this is machine learning as opposed to just programming. Then, of course, there are things I want to compare machine learning, say, as opposed to just what humans can do, and that's also something you just mentioned. Another good reason is that, so this is why should machine learn, but why not just use humans? And that is for tasks that require experience with amounts of data that are beyond human capabilities. So if I want to learn tasks like you write a query in Google and you want to see order the results in some sensible way. So Google does it by going through huge amounts of data and queries and ad placement on the web page. You type your request and you get a series of ads. And Google is making money if anybody clicks on those ads. So it's very important to them that the ad that they bring up to you will be relevant to your query. But the reason that humans cannot do it without machine learning is that in order to find an optimal ad placement, you need to go through huge amounts of data, huge amounts of prior data that was collected by Google from people asking queries and clicking on ads. And this amount of data is just too big for humans to conceive. So this is why some of the tasks that machine learning do, humans cannot do. And there are many such examples. So ads placement, genetic data, understanding the genetic data, lots and lots of examples that we use today with machine learning, that the reason we use machine learning is it's beyond human capabilities, understanding genetic data. And another, let me just mention one more important reason for the need for machine learning, and this is adaptivity. So if I have a program that can learn, the program can adapt to changing scenarios, to changing environment. And this is very important in some situations. So if you get your tablet and it has to understand your handwriting, I could not in the factory already program it to be able to decode the handwriting of everybody. So it gives you some assumption of what were you writing, you correct it, and it learns from the experience and it adapts to your personal handwriting. If we have a spam detector and the spammers are changing their behavior, the learning component in the development of a spam filter allows us to adapt to those changes. So, and there are more reasons why really, where exactly do we really need machine learning? So, I mean, I guess that I don't need to convince you that it's an important tool, right? So we can leave it at that. And okay, so there are all kinds of tasks that either humans do but cannot program, or humans cannot do but programs can, or we need adaptivity. For all of those, we need machine learning. And one more component in my introduction before I get to the real beginning of work is to know that there are many types of learning. So many types of machine learning. I want to somehow to show you some kind of, give you a perspective of where in all these potential uses of machine learning we are going to focus in this course. So the first kind of tension that one can look at is between supervised versus unsupervised. So what do I mean by that? So supervised is the kind of learning in which the training data has an important component that is missing in the test data. So spam filter is a good example for that. The training data are emails that has the component that someone marked them as spam or not spam. The data on which you want to test does not have this. You have to edit yourself. So this is called supervised learning because on the training data you get supervision. Someone is telling you this was spam, that was not spam in your training. But there's also learning which is completely unsupervised, where the training and the test data look very much the same. So for example, if you want to do outlier detection, if you are, this is something which is very common in security applications. You are working in some company and you want to make sure that none of your workers is abusing the system. So you look at the log files of all the workers and what they're doing all day, and you're trying to detect outliers. If someone has a pattern of behavior that is very different than all the others, you think there's something to be investigated there. But this is completely unsupervised. It's not that someone is telling you that was good, that was wrong. You're just looking at all the data and try to find outliers. So outlier detection belongs to the unsupervised side. Similarly, clustering. If I look at data and I want to group my data in groups of similar objects, that then may be easier to handle. This is done completely without supervision. I don't have in my training data any labels or any information that will not be there in test data. The spam filtering, or if I want to detect any kind of, say I want to train a speech recognition program, the speech recognition training is supervised because you see the sound and I give you the correct text. Then when you're at test time, you just see the sound and you don't get the correct text. So this is one big component along which there is many different scenarios. There's also an intermediate scenario which is called reinforcement learning. In which you do not get full supervision, but you get some supervision. It's sitting between these two. For example, if I want a program that will learn how to play chess. So you know that there are programs that can just watch games and see whether who won, and from that it learns how to play. But you would think this is supervised because the program watches a game and then knows, someone tells it who won the game, and the program learns how to play. But in what sense is it not fully supervised? Yes?
You don't have immediate feedback on the moves that it makes.
Right, you don't have immediate feedback on the move. The program eventually will have to learn which moves to take. And nobody labels the moves. You only label at the end of the game who won the game. So this is kind of sitting in between. We do get some supervision. We know who won the game, but we don't get immediate supervision for the type of task we'll have to test on. We'll have to test on did we move a good move or not. So this is called reinforcement learning. So this is one kind of coordinate along which there are many different learning stuff. And in this course, we will mainly talk about supervised learning. We will talk a little bit about unsupervised learning and not at all about reinforcement learning. Although all of those are important areas in machine learning. Another important component is batch versus online. So what do I mean by batch versus online? In batch learning, you get all your training data in advance, and you can just chew on it, do it whatever you want, and then you must come up with a conclusion. With online learning, you have to respond as you learn. So you come to a new environment, you have to start behaving. You don't have time to just sit on the side and watch people for a long time and learn how you should behave. You have to start behaving right from, and you make mistakes. You inevitably make mistakes. So in online learning, you kind of learn from your mistakes. You learn as you go, you make mistakes, you're trying to have a program that will make as few mistakes as possible as it learns. So this is the online versus batch. We will talk a little bit about online, but we'll mostly talk about batch learning. just because in some sense it's simpler to describe, but also talk about online learning. Other two important components are what kind of teacher do you have. So another component is cooperative to indifferent to adversarial teacher. So when you learn something and it's supervised, you have some kind of who is giving you the experience. And the experience could come from a cooperative teacher, someone who is trying to teach you how to do things. So they give you instructive examples. You get examples that are tailored to be as useful as possible. The indifferent scenario is a scenario in which you are in nature and things are just happening and you have no control of it, and nature doesn't intend to either teach you or prevent you from learning, and you're trying to learn from indifferent data that is generated without any connection to your learning. And there is also the scenario of adversarial learning, because if I'm generating spam and I want to prevent you from detecting my spam, I will generate the spam in a way that will try to mislead the learner as much as possible. So this is also a very important kind of coordinate, and in this coordinate we will mostly focus on the indifferent scenario, on the scenario in which we are learning from nature, we are learning from an environment that is indifferent to us. And the last component I want to mention, there are more, but I just want to give you some kind of a perspective of where we're going to be, is how is the learner going to be. So learner can be passive versus active learner. So what do I mean by passive versus active? A passive learner just watches the environment and sees what happens. An active learner can just perform experiments, design experiments in order to learn better. So you can think of it as in both situations, even happens when you think about a physicist. If you try to understand the physics of the world, you can do experiments with dropping apples and be active. But if you want to learn about the stars and what forces control them, you cannot do an experiment by deleting the sun and see how the planets will now behave without the sun, then introducing the sun again and do some kind of active. So there is the passive versus the active type of learning, and we will focus in the course on the passive. Also, we will mention a little bit active learning maybe at the end. So this is kind of where we are going to be in the big picture of learning. Finally, to end the introduction, I want to tell you a little bit about the relationship to other topics, courses, subjects that you might have studied, and about the nature of this course. So relationship to other fields or subjects. So first of all, I think the most obvious thing is that we are definitely related to AI, to artificial intelligence, but there are also some clear differences. We are related to artificial intelligence because when you have a program that learns, it's a program, so it's artificial, and learning, it does some kind of an activity which resembles the activity of intelligence. So we can say it falls within artificial intelligence. But well, there are also some important differences, and I think the two main important differences is one is that we are going beyond what humans, animals can do. We are trying to have programs that will take advantage of what computers do and animals cannot. So we are going well beyond what humans or animals can do, and we're not trying to imitate them. We're not trying to see how do humans do it, let's try to imitate it. We're trying to be as efficient as possible with programs. The other big difference from AI is that if any of you took courses in AI, the nature, the feeling of it is going to be different. Because this area is very rigorous, very mathematical, and definitely the nature of the course. So it's going to be different than AI in the sense that we're not going to talk about heuristics, we're not going to talk about things that feel right, that happen to work sometimes. We are going to do a full, complete mathematical analysis of what we're doing. Another very related field is, of course, algorithms and complexity. One of the big bottlenecks to the success, and we will see very soon why this is the real bottleneck to the success of machine learning, is the requirements of runtime. Many algorithms can be shown to have a lot of promise, but they get stuck because they require too much running time. So we will have to analyze efficient algorithms and their computational complexity, how much running time they need. Yes?
What kind of math are we going to use? Is it like more stats?
Yeah, so that's what I'm going to talk about. So we're going to, stats is relevant, statistics is relevant. We are going to use some linear algebra. We're going to use combinatorics and some optimization. But, okay, before you get scared, so we're going to use components from each of those. But before you get scared, I mean, I do have to assume that you know some linear algebra, that you know what is a vector space and the rank of a matrix and things like that. I'm going to assume that you know some basic statistics, but I'm going to, most of the things that we're going to need, I'm going to teach. And especially with statistics, it's very related to statistics, but we are different from statistics in several important ways which are worthwhile mentioning. So the first respect, of course, is that we are doing algorithmic statistics, stats. So we care about the algorithmic part that statisticians usually don't look at. How do you make a program do the statistics, not the human do the statistics? And the second, maybe more concrete thing is that we are going to be distribution free. So this is an important component, especially for this course. So what do I mean by distribution free? By distribution free, you see that how many of you have taken some course in statistics? Almost everybody, right? So in statistics, you take course in statistics that tell you about all kinds of distributions. Normal distribution, Gaussian distribution, binomial distribution. And they analyze what is happening when you have data that is generated by such distributions. In machine learning, we are taking a different approach. We're saying, I have no clue how spam is being generated. Nobody promises me that it's generated by a normal distribution or binomial distribution or whatever, Dirichlet distribution, whatever sophisticated type of distribution. So we want to have algorithms that will work regardless of how the data is generated, which is a much stronger and different requirement than in classical statistics. So the distribution freeness is a big difference. Yes? We will. This is kind of the tools that we'll be using. I'll mention it in a second. Right. And then the other component in which we are really different than classical statistics is we are interested in finite samples. So in statistics, you often see asymptotics, like the law of large numbers tells you that as the sample sizes go to infinity, things will behave nicely. But when we want to be practical, it's not good enough for us to do things as samples go to infinity. The rat cannot survive if I'll give it a guarantee that if tasting samples after go to infinity, then eventually you will learn to detect what is poison and what is not poison. We need much more concrete finite sample guarantees. And that's another big difference between what we are doing in statistics. But these are the relevant components. I think in terms of background that you need to know something about algorithmic and complexity, what is polynomial time, and some basic algorithms. You need to know some basic algebra, but mainly you have to feel confident, not to be scared for mathematics. I will teach you basically everything that we need, but you have to be in a mind frame that you're open to learning math. You're not intimidated by it. I will be very open to explaining and trying to clarify anything which is not obvious and taking a lot of time. But that's the type of course it's going to be. OK. As for the course outline of the course, so we are going to start by talking about principles. And in particular, we are going to talk about principles of the type of learning that I was looking at: supervised, batch, and so on, this type of learning. And we are starting by trying to understand the principles behind it. Then the next phase is going to be algorithms, or let me call it algorithmic paradigms. And by algorithmic paradigms, we will just familiarize ourselves with some of the most important tools of the trade of machine learning. So there's going to be support vector machines, and there are going to be neural networks, and we are going to talk about decision trees and some other big tools which are very important in the field. And we are going to connect them to the principles that we have learned before. So the aim is to be able to understand when is a specific tool useful for your application, under what conditions can you trust it, and so on. So the second part, we'll talk about some algorithmic paradigms. And in the third part, we'll talk about extensions to other types of learning. So as I described before, there are many types, many coordinates along which you can choose your task. We will focus on the supervised, batch, indifferent nature, passive learner. At the third part, we will talk about other combinations as well. So this is roughly the program for the course. I think that is as far as my introduction goes. Yeah. So any questions at this point? Yes?
So you said it's a purely theoretical course. So what kind of project do you expect?
Oh, so what kind of project? You already jumped to the project. So yeah. So I think that the simplest type of project will be that you read some research papers and summarize them. That's the simplest thing. The more exciting type is when you come across, there are lots. This is a relatively very young area. Machine learning, as we know it today, started with Valiant, Les Valiant, he just got Turing Award a couple of years ago, and he started this in a paper in '84. So this is now the 30th birthday of machine learning. It's a very young area. Lots, and the applications are coming up, more and more and more applications. As with more applications, we realize that there are many subdomains that we don't fully understand. So if any of you, any direction in which you take it, which was not developed before, and there are many such directions, just thinking about it and describing your thoughts can be a good project too. Okay? Any other questions on the general outline? Yes?
Do the grads also have to pass the final?
Yeah, yeah. Everybody has to pass the final. For the grads, the final is only 40%, but with failing it, you don't pass the course. You don't get the credit for the course. Right. Yeah, so that's the big cloud at the end of the... But I will try to have the assignments as similar, or I try to make the final as similar to the assignments as possible. So if you manage to overcome the assignments, you're in good shape for the final. Any other questions on this general term? Yes?
I have the problem with the learning with one example with rats, or because, well, you know, like one example is not statistically relevant.
Right. But we will not, I don't want to dive into things now. We'll talk about what can and cannot be done and how many examples you need. That's a very interesting issue. You could use it as also as a topic for a project if you will not be satisfied with the answer that will be given here. Any more general questions? Yes?
When would you be releasing the assignments?
What? Yeah, so I don't have now the specific dates for the assignments, but there are going to be 4 assignments. The first one is going to be in 2 weeks, and there will roughly be in 2 weeks, 2 to 3 weeks between them. And the book really covers everything it will do and more. So I encourage you to get hold of the book. I think that I get something like $1 from each purchase of the book. So if you all buy it, I can afford some kind of a lunch at Williams. Okay. So we have 10 minutes, and let me start with something a little bit more concrete. So to get more concrete, I will go along a slightly different example than somewhat different example than the spam example, an example in which we understand things better. And the example that I want to start with as a lead for the formalism that we'll start developing is the example of papaya testing. Okay, so what is the story of papaya tasting? The story of papaya is a real story. What, about 15 years ago, I did a tour around the world with my kids, and we got to some island in the Pacific. And this small island, turns out that the major component of the food there is papayas. They don't have agriculture. It's a volcanic island. They just have the trees that grow papayas and fish. And we never had papayas before. So you have to learn which papayas are tasty or not. So I want to discuss this example of how can you learn from examples, from experience, to figure out which papayas to buy and which papayas to leave behind. Okay? So what are the components that we need for this? So first of all, what is the training data? So I'm using here some kind of knowledge about relevant information. I assume when I look at the papaya, there are lots of things that you're looking at a papaya at the market. You want to know whether you want to buy it or not. I have to pick some relevant features that I believe will be correlated with the taste. So the 2 features that I pick for the papaya is the color, that can move from dark green to red or brown red, and the softness. Right? It can move from rock hard to completely mushy. I don't know how to spell mushy, but say something like this. So the first component I need is each papaya. I want to describe it. I want to take a papaya and represent it by two coordinates, just its color and its softness. So every papaya, the first thing I do, I represent every papaya as a point in a two-dimensional space. I have two dimensions that I can scale, and I represent every papaya by these two dimensions, and I forget everything else about the papaya. So the first component that I need is what is going to be my training data. And my training data are going to be of the form x1, y1 up to xm, ym. We sometimes call it a sample and designate it with s, where xi belongs to R2 because it's a two real numbers, the softness and the color. And the yi belong to, they're just binary. Say tasty, non-tasty. Just two values. So my input are those two coordinates of the papaya and the one bit for the taste. Right? And so this is my training data. My domain set is just this space R2. So say it's the unit interval 0, 1 square. Every papaya is represented by a point in the unit cube, which designates the color and the softness. So I have my domain space, I have my training data, I have my label set, as I already mentioned. My label set is just binary. It's a set consists of tasty, not tasty. And what is going to be my output? So I'm just turning the problem of learning the taste of papayas into a mathematical problem. So my output is going to be just a function. It's a function f that goes from my domain, from 0, 1 square, to tasty, not tasty. So my output, I get this training data. My output should be a rule that tells me when I examine a papaya and detect its color and softness, this is called a prediction rule. Prediction rule. This prediction rule is trying to tell me, is the papaya that I see now, is it going to be tasty or not? And as you see, this is supervised learning because my training data has labels. My training data is the papayas that I've already tasted, and I know if they were tasty or not. But when I make my prediction, I'm standing in the market, and I haven't tasted the papaya, and I have to buy it just based on the color and softness. Okay? So this is kind of the mathematical framework. And now we have to make some assumptions in order to be able to have any hope of learning. So my first assumption is about the data generation. So how is the data generated? So I make here an assumption about data generation. I assume that the examples that I tasted so far were randomly generated. I didn't pick them, they were randomly generated. It may not exactly reflect reality, but in many situations it is a realistic assumption. So, and furthermore, we'll make a simplifying assumption. So the first assumption is that the data is randomly generated, my training data. The second assumption that I'm going to make is a very strong assumption, and this is called the realizability assumption. Realizability by rectangles. So what do I mean by that? What I'm assuming here is a very strong assumption that there exists some axis-aligned rectangle of tasty papayas. That the tasty papayas are all the papayas that are not too hard and not too soft and not too green and not too red. So my goal, I'm making the assumption that there is such a rectangle that determines the tasty papayas. It is, of course, a crude assumption, but it is some approximation to what we really do in reality. And now, what I'm trying to learn is the parameters of this rectangle. So I'm getting papayas, and I'm trying to learn what will be a good rectangle for using to predict the taste of papaya. So the last component that I want to introduce before we start searching for an algorithm that will be able to do it is how do I evaluate the success of such a function? So you see, my data is those points which are labeled tasty or not tasty. My algorithm takes those points and outputs some prediction function. How do I measure the success of such a prediction function? So the last component I want to introduce is the measure of success. And the measure of success that I'm going to use is the probability of making an error on a randomly generated papaya. So it is going to be the probability of my predictor f to err on a randomly generated papaya. So I want an algorithm that will take such training examples, and assuming the training examples were generated by some random process, the algorithm will come up with a predictor that has high probability of success under the same distribution, under the same data distribution. So I do assume that I have the same data distribution at training, at test, and at the test, but I don't assume anything about the nature of distribution. I'm not saying it's Gaussian. I'm not saying it's normal. I don't assume anything of that kind about the distribution. Okay, so this is the game board on which, or the sandbox with which we are going to start playing, and we will start doing formal analysis of this on Friday. Thank you.